Okay, so hydraulic fracturing is a means of production enhancement which is done by a method called stimulation. Okay, so in this process, what usually obtained is a fluid that is mixed with propane is injected into the reservoir at a pressure that is higher than the fracture pressure of that reservoir. This is done in order to create highly conductive path within the reservoir that will ease the migration of fluids from our reservoir into the borehole. These hydraulic fracturing techniques usually apply to treat the area around the borehole that must have been damaged. We have talked about the skin effect so many times. We have mentioned the skin effect so many times here. And we have talked about what is the main cause of the skin. Next week, we are still going to look at it again in detail because next we are going to look at I think it's another method of stimulation, which is called acid treatment, and how we could do some simulations on acid treatment. So all of these acid treatment and hydraulic fracturing, all of them are means of enhancing production, which is to create some high conductive pathways within the reservoir that will ease the migration of fluid. These high conductive pathways is probably done to bypass some damage that have been created close to our well bore. This damage, we will probably look at it in detail next week. I don't want us to talk about this damage, but we must have been talking about all of these skin effects and how it is treated. So if I have here, for example, this is my borehole and this is my reservoir. I have this zone around the borehole that is very close to the borehole that has been damaged. So fluid cannot easily flow from the reservoir into this well bore because at this particular point, there is some additional or extra pressure drop that is due to the blockage of the pore spaces by the blockage of the pore spaces within this particular region around the reservoir. So generally, when you carry out hydraulic fracturing, you inject this fluid that is filled with propant into the reservoir at high pressure. The pressure should be greater than the fracture pressure. The fracture pressure is basically the pressure above which that formation can easily be fractured. So when you inject that particular combination into the reservoir, it now creates hydraulic fracture pathways where fluid can easily flow now into the reservoir. So after this particular exercise, if you carry out an analysis of this particular reservoir, you realize that it has a negative skin because I've talked about the skin, I talk about positive skin and negative skin. Positive skin simply means that there is a damage within the reservoir. Negative skin simply means that the area now is becoming so productive, so conductive. We have a very high permeability around that particular zone. And this high permeability can only be caused, can only be as a result of these stimulation processes after maybe a hydraulic fracturing job must have taken place in that particular reservoir. So we are going to first of all start by looking at the basics. We are going to start by looking at the basics of this hydraulic fracturing so that once we get into the software, whatever we see there, we should be able to interpret it. So basically, when after the hydraulic fracturing job, like what we have here, after you must have inject the fluid filled with propane into the reservoir, you may have a fractured area that looks exactly like this shape. It may not be as exactly like this because you have different models This one is just a geometry of a particular model, which is called the PKN model. So you may have a geometry that looks like this. So from there, you should be able to characterize the height of the hydraulic fracture, because when you look at what we have here, the fracturing is not in the entire reservoir. This is our entire reservoir, where you realize that only this particular zone from here, from this point to this point, is perforated. So the fracturing fluid is injected in this perforated zone. This is the area where the fluid finds its way into the reservoir. And it has to be organized in such a way that you don't fracture a zone that is not required. Because definitely, if this is my reservoir, I will expect that there is an oil-water contact around this particular point where I have my oil up and my water down. What I will need to do is to fracture only the oil zone, because I want the oil to migrate. I don't want to fracture the water zone because I don't want to increase the water cut. Because immediately this hydraulic fracturing touches the water zone, we now start having high water production. So the job has to be organized in such a way that it has to minimize the amount of water that is produced. So at the end of that, we may have this shape. So from there, we can characterize the height of the hydraulic fracturing. We have the length, which is generally called the fracture half length. We have the length, then we have the width of the fracture. So at the end of the day, after the hydraulic fracturing exercise, you should be able to give an analysis of all of these parameters within that hydraulic fracturing. Because generally, before the job is carried out, you have to do a simulation of what you expect to happen within the subsurface based on the geomechanical properties, because the geomechanical properties plays a huge role in hydraulic fracturing. Because if since you are injecting and pressure is the main factor that causes this fracture to be created, geomechanics has to come into play. We are going to see how all of that comes in. So this is another look out of how the fracture looks like after the hydraulic fracturing exercise. We talked about the heights. We have talked about the height. We have talked about the width and the hydraulic fractured width and all of that. They are hydraulic fracturing half length. Okay, so this is another lookout of how the hydraulic fracturing job will look like at the end of the day. We have talked about this already, the half length, the hydraulic fracturing half length. We have the width, and then we have the height. Looking at it in one dimension, you're going to see something like that. You're going to see something like that. So after you must have created this particular fracture, you now have two types of flow that is existing within that system. I may use the word dual porosity. We may have a dual porosity system where fluid, first of all, have to flow from the reservoir, which is acting as a matrix, then from the reservoir into the fracture zone, then it now flows from the fracture zone into our borehole. So from there, we can actually see the fracture half length. We can actually see the fracture half length. So there are various domains in which hydraulic fracturing can be exercised. It must not only be in a low permeability domain. We can also apply hydraulic fracturing also in a high permeability domain, but with different objective. So if I have, for example, a low permeability rock, and I have to carry out hydraulic fracturing. If it's a sandstone, what I'm going to carry out is a propan frac. That means I'm fracking the rock using a propan. You're using a propan. But if it is in a carbonate, you have to do what we call acid frac. We have to do acid fracking. Acid fracking is another type of acid treatment, but it doesn't only treat the region, but it causes fracturing. That means you're injecting the acid at a pressure that is higher than the fracture pressure. It goes in to treat the formation and also fracture the formation. Because in acid treatment, what is done generally is that it is injected at a pressure that is lower than the fracture pressure, so that the acid goes in to treat the formation. to treat and remove those chemicals that are blocking the pore spaces, so that it washes away all those chemicals that are blocking the pore spaces, and at the end of the day, that region become porous. But acid frac can also be carried out in a situation where it is not only injected to do the treatment, but the aim is also to create some highly conductive pathways. So you're doing two things at the same time. So for a carbonate reservoir, we can do that. All right, I don't want to talk more about the acid treatment because we'll talk about it tomorrow. And then for high permeability reservoir, what is mostly done is acid treatment. What is mostly carried out is acid treatment. You cannot be carrying out a propan frac in a high permeability reservoir. And this acid treatment is what we will talk about next week. I think that's the last week of our summer internship. So we are going to discuss this next week. All right, so what are the various objectives of carrying out this hydraulic fracturing? We have already mentioned a few, which we'll talk about some of them here. We have to bypass the near ball damage. When they talk of bypassing, it simply means that you are not treating the damage, but you're creating a highly conductive pathway where fluids can also pass while the damage is still existing. So if I take us back to around this area, for example, if this is my damage, not if this is my damage, because it is indicated there as my damage. When I inject this fluid into the reservoir at high pressure, when it gets into the reservoir at high pressure, it creates this particular fracture that we are seeing. But when I look at what I have here, the damage is still existing, but I have some highly conductive pathways that have been created. These highly conductive pathways have been created that bypasses this damage but doesn't treat the damage. But for acid treatment is coming in to treat this damage. It doesn't bypass it. I'm talking specifically for a sandstone reservoir, because even for acid treatment in a carbonate reservoir, you cannot treat this particular area. You are bypassing the damage. You just create some kind of activity that gives pathway for fluid to flow, but the damage itself is still existing around that particular zone. So that's the meaning of bypassing the damage. To increase the drainage area and change the flow regime. So if you realize that in this particular case, you have now changed the flow regime, because the flow regime now is now becoming more linear. In this case, we know the various types of flow regime. We have the radial flow. Without this damage, fluid will be flowing into this borehole from different directions. It will be flowing into this borehole from different directions. But when you create this hydraulic fracturing, what is happening is that the flow is more or less linear, because the fluid is now flowing into the fracture. Then from the fracture, the fluid is now flowing into the borehole. The flowing of the fluid from the reservoir into the borehole is in a linear manner. So that's more or less linear flow. So you can also carry out hydraulic fracturing to increase the drainage area and to change the flow regime. To connect with natural fractures, we may have different natural fractures within the particular reservoir. When you look at what we have here, we have different fractures that radiate in different directions. There may not be a clear connection between this fracture in order to ease the flow of fluid into the borehole. So what will happen is, when you create this hydraulic fracturing, when I fracture this particular zone, I fracture this particular zone also, it now connects all these fractures, and fluids can now flow from each of the fractures into the main fracture that has been created, into the hydraulic fracture that has been created. Then from there now, it now moves into the borehole. It may connect with disconnected zone or formation. We may have these sand lenses that exist within the formation. We all know what are sand lenses that exist within the formation. So when you create a hydraulic fracturing, the hydraulic fracturing goes into the reservoir to connect with each of these sand lenses, so that they can now connect together and ease the flow of fluid from the sand lenses into the reservoir. So you have different reasons why they may carry out hydraulic fracturing. It may not only be to bypass the damage, it may be to connect with thin layers. So you may have different thin layers, so many thin layers within that particular zone that contains hydrocarbon, and they may want to carry out hydraulic fracturing in order to connect each of these thin layer to a major fracture that will now lead into the well bore. So these are the various reasons why hydraulic fracturing may be carried out. So generally, this is just what we have really talked about to change the flow regime. Without the fracturing, we are having a radial flow, fluid flowing from different direction. But after the fracturing, we are having a bilinear flow. We are having a bilinear flow regime within that particular system. So generally, without this particular damage within the reservoir, I will Okay, so generally, if I have a reservoir that does not have a particular damage around that particular zone, you realize that this is generally our pressure profile from the reservoir pressure to our bottom hole flowing pressure. But if there is a damage around that particular well bore, you realize that as the fluid gets into that particular zone where that damage exists, there is an extra pressure drop as a result of this damage, as a result of blockage of pore spaces within this particular zone. There exists an extra pressure drop within that particular zone. This extra pressure drop now is due to this damage. There are various ways in which this particular damage can be characterized, maybe by using well test analysis, which is pressure transient analysis. I think we did a little bit of well test analysis using Excel. I think that was in week 3 or week 4, like that. I think we did an analysis how you can use the build-up test or you can use the drawdown test in order to characterize the reservoir and determine the skin factor. From the skin factor, you may now have to decide if you have to perform hydraulic fracturing or not. So if you're carrying out a project on this hydraulic fracturing, they expect that at least you should tell the people what is the skin effect before the hydraulic fracturing and what the skin effect will be after the hydraulic fracturing, to show that there is some kind of production enhancement at the end of the day. So this is basically what is happening during the hydraulic fracturing exercise. We have our fluids that is filled with propant. I've been using the word propant. We'll talk about it later. When you inject it into the reservoir, it now creates these highly conductive pathways. So what will now happen is, after you have created this highly conductive flow path, the pressure regime now is not going back to the original position, but it is going back at a higher position to show that there is less pressure drop within this particular zone. This less pressure drop is as a result of the area becoming more conductive than its natural state. So the area now is not going back to its natural state, but it becomes more conductive than its natural state. All right, so from this is our hydraulic fracturing. This is our hydraulic fracture that we have created. From there, we can analyze what we call the fracture conductivity. The fracture conductivity is calculated by this formula. We have the fracture permeability, because after the hydraulic fracturing exercise, you should be able to get the conductivity of the hydraulic frac, and then you should be able to know the width, the fracture width. Then we know our formation permeability, that's the permeability of the formation in general. So from there, we should be able to calculate the hydraulic conductivity. All right. So ideally, we want this hydraulic conductivity to be around 1, All right, so after our hydraulic fracturing job, we need to analyze the entire area to be sure that there is some kind of production enhancement. So before the hydraulic fracturing job, we have our flow area. We can use this Darcy's law for radial flow to calculate the rate at which the fluid is dropping into our well bore. Then after our hydraulic fracturing job, we can now use this particular formula in order to do the analysis. Okay. So basically, if we look at this formula, this is a natural formula in a situation where there is no damage. But this is the formula in a situation where I have a damage because I now have a skin. So if the skin is positive, this entire denominator becomes higher. And if this entire denominator increases, what will happen is that our flow rate will decrease, because definitely our flow rate should be inversely proportional to the skin. After the hydraulic fracturing job, what we expect now is a negative skin. Once we have a negative skin, when we put a negative value here, the negative value is coming in to reduce this denominator. When it reduces this denominator, our flow rate is going to increase. So we have to use this particular equation to analyze the flow rate or the productivity of the system before the hydraulic fracturing job. And we can also use the same equation to analyze the productivity of that system after the hydraulic fracturing job. After we must have analyzed what our skin effect is after the hydraulic fracturing job. So we may also look at the fold of increase. The fold of increase now is how much has the productivity index increases. We now look at the productivity index after the hydraulic fracturing job divided by the productivity index before the hydraulic fracturing job. And if you remember or you recall the formula of productivity index that we have been using all through this internship, you realize that if I take this divided by this, probably with productivity index, it is flow rate divided by change in pressure. So when I calculate productivity index, generally this pressure change will not be existing in that formula of productivity index. So to get the fold of increase, this is our formula that has to be applied. Now, generally, after the hydraulic fracturing, what you need to do now is to analyze the skin effect. What is the skin effect of our system to know if there is some kind of an increase in productivity or not? Generally, what will easily be applied is well test analysis. They can use well test analysis in order to characterize the conductive path, to know its productivity, to calculate its permeability, and to know the skin effect. But if I don't have that particular test, I can use some kind of a correlation in order to determine the skin. But if you look at what we are having here, is some kind of an approximation. If I am dealing with low permeability reservoir, then what I will do is I will use this particular correlation in order to calculate the skin effects after the hydraulic fracturing job. If I'm dealing with high permeability reservoir, remember I have talked about hydraulic fracturing in low permeability and in high permeability. So if I'm dealing with high permeability reservoir, I will definitely use this formula in order to characterize this the skin effects after the damage. So if you're writing a project on this, what you have to use after the hydraulic fracturing job will be this correlation, because you need to demonstrate that after the hydraulic fracturing job, there is some kind of an improvement in productivity. So since probably we will not be able to carry out the well test analysis because you are doing a classroom project, what you have to do is to use this correlation in order to determine the skin effect after all of that. All right, so I think this is just an exercise in order to calculate the skin. This is just an exercise in order to calculate the skin. They have given the reservoir permeability. they have given the fracture permeability, they have given the fracture width, they have given the fracture half length, and they have given the well bore radius. And they want you to calculate the fracture conductivity and also to calculate the skin, and also to calculate the skin. So this is just an exercise that has been given. All right. So we see exactly how this hydraulic fracturing job is taking place within a low permeability and within the high permeability. If I have a high permeability reservoir, I will have the tendency of this particular fluid to fracture not only the reservoir, but to expand beyond the reservoir. So I have a smaller zone that has been created, that has been fractured, but it has a higher fracture height. It has a higher fracture height. But for a low permeability reservoir, you realize that you have a higher fracture half length than this fracture height. So when you compare the two, you realize that this particular case will be higher than in this particular case. So we have to also bring in the aspect of geomechanics to talk about a little bit of geomechanics, because this geomechanics also plays a huge role in this hydraulic fracturing exercise. If we don't incorporate this geomechanical aspect into it, we will not be able to fully understand exactly how this fracture will take place. Of course, there is no way, even inside our software FracPro that we are going to do the simulation, there is no way you can even proceed if you don't try to give some kind of geomechanical characteristics of the zone. Not only the zone, even the zone that you want to fracture and even its neighboring zone, because it will determine whether the fracture will extend to other zone or not, especially when we are doing 3D simulation. So for our basic geomechanical analysis, we know of some basic gradient that we have. We have the lithostatic gradient, we have the fracture gradient, and we have the hydrostatic gradient. For lithostatic pressure, we know what lithostatic pressure is all about. Lithostatic pressure, that's a pressure due to the weight of the overlying material on the reservoir. We have a particular reservoir, we are looking at the weight of that underlying of the overlying material on that reservoir, and definitely it will depend on the depth of the reservoir. That means it will depend on the thickness of the material above that our reservoir. So generally, there is this general way in which the pressure increases with depth. That's what we bring the term gradient, because the gradient is in terms of PSI per foot. So there's this general way in which the gradient will increase gradually with depth. But we know that the rock of the earth, they are not uniform. So we don't expect that the lithostatic gradient in one region must always be the same. We may have this particular general trend that has been given, that generally it is approximately 1, but doesn't mean that it must always be 1. We may have 0.9, 0.95 in some areas and all of that, depending on the type of rock that we have in that particular area, because this lithostatic pressure depends largely on the density. So the density of the rock also matters. So as you are moving downward also, we also have this, our fracture gradient also. The fracture gradient is telling us how much force or how much pressure is needed in order to fracture that particular rock. As you're moving deeper and deeper, the hydraulic fracture gradient, the hydraulic fracture pressure is increasing and increasing. All right. And this geomechanical aspect, even though it is out of what we are discussing now, is also very important in our drilling activities, because they always have what we call the drilling, the mud window. They have this term that they use in drilling that is called the mud window. That means you have to do an analysis to ensure, because there is this mud that is injected inside our borehole has a pressure. And remember that they always say the pressure is greater than our pore pressure, so that it stops the formation fluid from getting into the reservoir, so that it doesn't cause a kick. It doesn't cause this kick. That means the uncontrolled fluid of hydrocarbon during our drilling process. But in order for this pressure to be greater, generally I've said we make it to be greater. than our pore pressure. But you have to be very careful. You don't increase the pressure to be greater than the fracture pressure, because if you increase it to be greater than the fracture pressure, it is going to go a lot way to create fracture within our reservoir and even other formations, which is not desirable, because when that is done, it might create some kind of instability within our borehole. So there is this term that is used in drilling, which is called mud window. So you have to make sure that the mud pressure is greater than the pore pressure and less than the fracture pressure. If the mud pressure, if the fracture pressure and the pore pressure are not too far away from each other, they now bring in the term managed pressure drilling. You have to now be, there is some kind of a high-tech drilling in such a way that they need high-tech specialists in order to carry out such drilling. It's not everybody that can, or any company that can carry out such drilling, because there is a narrow window between our pressure, our pore pressure, and our fracture pressure. And you have to manage the pressure within each zone in such a way that at the same time, it is higher than the pore pressure and lower than the fracture pressure. That is out of what we are discussing at the moment, because we are talking about hydraulic fracturing. All right, so there are some basic terms that I believe we should be comfortable with these terms. We have our stress, we have our strain, and when we have our Poisson ratio. If you look at this particular block, for example, we assume that it is our reservoir. When they talk of the term Poisson ratio, I will not talk about stress and strain. I believe that we must have heard about this from basic physics right up to this level. So I'll talk about Poisson ratio because most students tend not to understand exactly what Poisson ratio is all about. So when you apply stress on a material, that material compresses. As it is compressing, it is extending in the y direction, because I have two directions here. I have probably my y direction, and in this case, they have called it the x direction. We have the x direction here. Then we have the y direction. This is our y direction, which is in the horizontal manner. So as you are compressing the material, it is not only compressing in the x direction, but it is extending also in the y direction. It's just like you hold something that is soft like a foam. As you squeeze that foam, as it is reducing in volume in one direction, it is increasing in volume in the other direction. So our Poisson ratio now is the change in one direction with respect to the change in the other direction. The extension in the y direction with respect to the extension in the x direction. So that is our Poisson ratio. So the Poisson ratio is coming in to tell us how tough the material is. How tough is the material? So when I reduce it in the x direction, how much change does it comes in the y direction? So this is a very important parameter in our hydraulic fracturing job that you must input before the hydraulic fracturing exercise can actually take place. So generally, this is our stress-strain relationship that comes in to characterize our material, which you must have seen the Hooke's law and all of that. We must have seen all of this. So this is just coming in to tell us that it plays a very important role. We have our elastic domain, and then we have our plastic domain. So when the material is stressed right up to its yield point, or right up to its elastic limit, beyond the elastic limit, it doesn't obey Hooke's law again. You stress it, it will not go back to its original length. So we have our elastic regime, and then we have our plastic regime. And at the end of the plastic regime, the material fractures. So there are some materials that will have a high limit of plastic regime. Others will not have this high limit of plastic regime. I'll take, for example, we always use this common example of glass. Once you stress glass beyond its elastic limit, it doesn't behave in a plastic manner. It just simply cracks. So some materials will extend beyond this particular yield point larger than others will extend. That's why we now have to also incorporate what we call the Young modulus into it. How much energy is required to deform the rock. That is what Young modulus is all about. It's coming in to define how much energy is required to deform that particular rock. All right, so we have talked about this a lot. We have soft material and then we have the hard material. We are seeing what will happen if hydraulic fracturing is performed in a hard material. We see the manner in which the fracture width and the fracture height and all of that. In fact, the fracture geometry will look like, we see how the fracture geometry will look like. Yeah, we say it tends to transmit stress, high pump pressure, long, narrow. So the fracture, the geometry is long and narrow, while this one is short and wide. So I've already explained this. So this is the regime for a hard rock and a soft rock. So for shear modulus, these are things that also have to come in. What are the various changes that takes place in as the material is being stressed and all of that? So these are all aspects that needs to come in also. So we know that generally, if we have a rock that is in a cubic form like this within our reservoir, when that material is stressed, this stress is acting in different direction. The stress that is perpendicular to each of the surfaces of this particular rock sample is called our normal stress. So on each surface, we have three stresses that are acting on each surface. We have the normal stress that is acting perpendicular to the surface. Then we have two shear stress that is acting parallel to the surface. This normal stress is coming in to cause the material to deform, thereby causing what we call normal stress, normal strain. So we have normal strain and we have shear strain. That is why when you look at this particular diagram, when we are talking of shear modulus, the shear modulus now is causing the particle to deform, not to deform, but to change its shape. So it is coming in order to change the shape of that particular material. But our normal stress is coming in to change the size of the particle. So there are two things that is happening. We have change in shape and we have change in size. The normal stress is changing the shape, is changing the size, and the shear stress is changing the shape. But generally, in order to analyze our geomechanical system, they have to assume that each of these shear stress is zero. When each of these shear stress is zero, we now have three stresses that are acting on the material. We have one vertical stress and then we have two horizontal stresses. Remember, this stress is acting from this surface and it comes out on the other surface. So when this particular assumption takes place, we now talk of principal stresses. These principal stresses comes in only when these assumptions must have taken place. So I know that within a particular reservoir, I have three stresses that are acting on the rock sample. I have my vertical stress, which in this case is the overburden stress, or the lithostatic stress, which I have already talked about. Then I have two horizontal stresses. One of these stresses must be greater than the other. So I have a maximum horizontal stress and I have a minimum horizontal stress. This minimum horizontal stress is usually called the closure stress. The stress that is required to close the fracture. Remember, after this hydraulic fracturing, if care is not taken, the weight of the overlying material can close back the fracture and you have wasted energy and money for nothing. So that's the reason why a propan is used, so that at the end of the hydraulic fracturing exercise, the fracture that have been created has to remain open. So they have to use the propan. So you need to know what the amount of stress that is required in order to close this fracture. And usually it is our minimum horizontal stress. So we have here hydraulic fracturing will initiate and propagate with the least energy. So it is initiating in the direction of the least energy. That means it is initiating in the direction of the lowest stress. That's where the fracture is propagating. And generally, it will propagate in the direction of the minimum horizontal, the minimum principal stress, or the minimum horizontal stress. All right. So fracture, what we have here is talking about our fracture direction. Here we have our overburden stress. We have our overburden stress there. We have the maximum horizontal stress. Then we have our minimum horizontal stress, which is our least principal stress direction, which is the least principal stress direction. All right. So the shape of our hydraulic fracturing also depends a lot on, because we may have a situation where our overburden stress is the least stress in this particular system. The fact that they have talked about minimum horizontal stress does not mean that it is the lowest stress. You can have a situation where the overburden stress is lower than even the minimum horizontal stress. The minimum horizontal stress is with respect to this other stress. It doesn't necessarily mean that it should always be lower than all of them. Definitely, it should be lower than the maximum horizontal stress, but it is not a guarantee that it should be lower than our overburden stress. So all of this stress regime also will go a long way in defining the overall geometry of our hydraulic fracturing after the hydraulic fracturing job must have taken place. All right. All right, so this is a situation where look at this, exactly what I'm talking about. If you look at what we have here, in this particular case, the overburden stress is greater than the minimum horizontal stress. Is greater than the minimum horizontal stress. We look at the manner in which the hydraulic fracture is propagating. But if I come in this case, you realize that the overburden stress is the least principal stress. That means even the minimum horizontal stress is greater than the overburden stress. In this manner, you now see how the hydraulic fracture is propagating. So defining the stress regime, it goes a long way in giving us a good overall geometry that will define our system. Remember, we are doing simulation in order to see how this hydraulic fracture, will see how this activity will go on in a real situation. If I have to go and do the pumping, how do I expect this fracturing to propagate? How do I expect the overall geometry to be at the end of the day? So that's the reason why you are doing simulation. So this simulation generally comes in before the actual exercise must have taken place. So it usually comes in before the real exercise takes place. So we have different directions in which the hydraulic fracturing can exist depending on the direction or depending on which particular stress is higher. In this case, we may have our vertical stress is the highest. In this case, our maximum horizontal stress is the highest, and the vertical stress is higher than the minimum horizontal stress. And in this case, the minimum horizontal stress is higher than our overburden stress. So we can see how all of these will go a whole long way to define the geometry. Okay, so our next aspect now is to look at the propant. What are the various propant that can be used, and what does this propant do exactly in the overall job? Because the exercise is divided into various stages. What are these various stages, and at what stage does the propant comes in? Because the propant is coming in to fill the fracture that has been created, so that no matter the pressure of the overlying material, the fracture will not be closed up. So it is coming in to act as a resistance against the pressure that is trying to close up the fracture after the job. So this hydraulic fracturing, this propant also should be able to withstand the closure pressure. It should be able to withstand the closure pressure. So it should be a material that has a high resistance to pressure. Because if you bring a material that does not have this high resistance, the material is going to crush the material and then close back the fracture. So the material should be able to withstand this stress, so that at the end of the day, this is how this picture that we are looking at, this is how exactly the fracture will look like. We have our pore spaces that remain within that particular system that has not been closed up by our closure pressure. All right, so first thing is to first of all give an analysis of the size of the propan. So the propans are always analyzed in terms of their size. We may analyze them in terms of their mesh size. We have 12/18, 12/20, 20/40. 20/40 is the most widely used. So if I use 20/40, it means that because you cannot have a propan that has a unique size, it's practically impossible for you to have a propan that has a unique size. You may have it over a range of sizes. So when we talk of 20/40, it means that the propan can pass through a 20 mesh, but it will not pass through a 40. So it will pass through 20, but the 40 mesh is going to hold them. So it means that the size of the propan lies between 20 mesh and 40 mesh. So we have different types of propan. Some of them are synthetic propan, some of them are natural propan. So we have these high strength ceramic propans. These are synthetic propans. We may have some other cheap propans that we have the bronzy sand and we have the white sand. This sand, I think, is most widely distributed in, I think, is it in the beach of Miami or something like that. These are natural propan, but these ones are synthetic. So the synthetic propan generally should be more expensive than the natural propan. And they are tougher than the natural propan. They are tougher than the natural propan. So in order for you to carry out this job, you have to know exactly what type of propan you need. While I look at the propan in the West Texas, dune sands, you know that West Texas is having this kind of desert environment. It's found in a desert environment. Then you have this in the Canadian glacier sand. This is the Canadian glacier sand. Then you have the Arkansas River sand. You have the Arkansas River sand. These are the type of propan that we have in those particular areas, which are natural propan that can easily be used. So from here, we can actually look at the strength of the propan and to see exactly how the strength of the propan can go. Well, let's start first with the size of the propan. How the size of the propan goes a long way to increase our permeability of the system. So you realize that if I have a 12/20 sand, I am having the highest permeability of that system. I'm having the highest permeability, and it is able to withstand the highest closure stress of that particular system. So as you're reducing the size of the propan, you are also reducing the productivity of that particular hydraulic fracturing after the hydraulic fracturing job. So the size distribution also matters. If I have a propan that has a uniform size, I expect to have a porosity of at least 45%, a propan porosity of at least 45% at the end of the day, which will increase our fracture permeability. But if I have an unevenly distributed propan, you now realize that the permeability at the end of the day is going to be lower than 30%. So you can see how various parameters of our propan can go a long way in giving us the characteristics of that particular hydraulic fracture after the hydraulic fracturing job. We might also look at the shape, the size of the propan. We have the roundness of the propan, the ferricity of the propan, and all of that. And we have a table here that is characterized, that the size of the propan is characterized in terms of roundness and ferricity. Then when we come to this particular graph, we can see how the size and all of that can go a long way to also give us a good permeability and all of that. So if I have a propan, once you have, let me start with this one first. Let me start with this one so that we don't mix up. When you have a propan that has a good shape, it goes a long way to withstand high closure stress. It goes a long way to withstand high closure stress. And this particular graph also is characterizing the strength of the propan. If I have a high strength propan, I'm going to have, it should be able to withstand high closure stress and will give us a higher permeability at the end of the day. So we can see how the various characteristics of the propan also is going a long way to give us a good characteristics of the hydraulic fracturing job. We can also look at the fracturing fluid. We can also look at the fracturing fluid because this propan definitely has to be mixed with fluid. And first of all, in our first stage, which is called the part stage, you have to first of all inject fluid into the reservoir before you inject the propan. So the fluid has to go in before the propan is coming in. So we have our fracturing fluid. What are the various types of fracturing fluid and what are the properties of this fracturing fluid? So the objective of a fracturing fluid is to deliver propan to the formation. So if you don't mix this fracturing fluid with propan, there is no way this propan will be able to move from the surface right down into the reservoir. So there are various characteristics of this fracturing fluid. We are talking about proper viscosity. It should be non-toxic, non-damaging, easy to use, low fluid loss, low friction, and all of that. So there are various characteristics of the fluid. So generally, this our propan, this our fluid is made up of water and other chemicals there. It's made up of propan, you may have surfactant, you may have KCl, the gelling agent, the scale inhibitor, the pH adjusting agent, and all of that. So all of these parameters are coming in depending on the analysis of the system. They may want to ensure that the fluid does not go and cause an additional damage. It doesn't go and cause some kind of scale formation because it is incompatible with the hydrocarbon within that particular system. So they may bring in a scale inhibitor and all of that. So this our fluid is made up of water, and then you have different chemicals that also come in to bring one or two parameters into existence. So our fluid may be oil-based or it may be water-based. So we must have seen all of this in our basic courses of drilling. Generally, our water-based is safe, it is available, and it's economical. Our oil-based is very, very expensive. That's a disadvantage of it. It's very, very expensive. It has a low interfacial tension. Yes, that means it can easily flow within the system. It has a low interfacial tension, and it is less damaging to clay. Oil will always damage, water will always damage scale. So each of them, they have their advantage, and then they have their disadvantage. So what the curve that we have here is showing us the trend that the trend of fluid that has been used from when all of this started right up to our present time. So originally, what was used was our oil-based. Originally, when all of this idea was initiated, what was used was oil-based. But as time went on, it was gradually shifting from oil-based into water-based. So now, how do we create our fracture model? How do we create our fracture model? So the first thing is for you to understand the geomechanical implication of that particular system. You have to understand the geomechanical implication. You have to ensure that your fracture is within the particular zone that you want. So this is the importance of our fracture width. If you go and you fracture this and the fracture occupies the entire reservoir, you realize that you must have penetrated into our water zone. And once you penetrate into our water zone, you will not only have oil production, but you also have water production. Then you have to also understand the strength of the material that surrounds the particular reservoir so that your fracturing does not go a long way to fracture zones that are not necessary, so that your fracturing will stay within the particular reservoir. So that's the importance of geomechanics. So they are talking of the importance of stress regime. You have to understand the stress regime. If I know the strength of the material above and below, I will inject the fluid with some kind of a care in such a way that the pressure that I inject does not go beyond the stress, the strength of the material above and below it, so that it doesn't fracture that particular area also. All right, so this is our geomechanical model and how to develop it. The first thing to develop your geomechanical model, you need the density and the sonic lock. We have already talked about a lot about our lock when we're doing our, that's the first week. We talked about our lock. So we have our density lock and sonic lock. From there, we can characterize it to obtain the shear modulus, the Poisson ratio. From that, we can get the dynamic Young modulus. From the dynamic Young modulus, we can get the static Young modulus. From the static Young modulus, we can get the overburden pressure. Then we can get the pore pressure. Then from all of this, we can now calculate the minimum horizontal stress, which is generally our closure stress, All right. So generally, we have different types of model that can be used to model or to simulate the behavior of the fluid. We have our 2D model and we have our 3D model. For 2D model, the most widely used is our PKN model and the KGD model. That is most widely used. So we have, this is the diagram of the PKN model and the KGD model, how it looks like at the end of the day. I think I have, okay, no, I don't have better shape. So you look at it, you realize that for this, the fracture height we have is like, I mean, oh, I don't need going back. But I think I showed the model for a hard rock and a soft rock. That model for a hard rock and a soft rock is more or less a description of the PKN model and the KGD model. For a PKN model, we have a fixed fracture height, we have an elliptical cross-section, we have elliptical shape, then we have the fracture half length is greater than the fracture height. The fracture half length, this is our fracture half length, is greater than 3 times the fracture height. Then for the KGD model, you realize that the fracture height is greater than the fracture half length. That means the fracture does not penetrate right deep into the formation. So these are the formulas that can be used to characterize, to calculate our fracture half length and our fracture width for each of the model. You realize that from here, we have what? We have the Young modulus that comes in. We have the Poisson ratio that comes in. We have our injection time, the time of injection that also comes in to define each of these parameters. All right, so we also have to define our pumping schedule. We also have to define our pumping schedule. How would the pumping go on? This is a typical description of our pumping schedule. What are we pumping at each stage? We have the part stage, we have the slurry stage. They have to pump the slurry, and then they have to now start increasing the size of the slurry. So if you come here, I think if you look at the propane type here, the propane type is our sand. We look at the elapsed time, the fluid type, the clean volume that is pumped, the pumpant concentration. So you realize that the main parameter that is changing at each stage is our propane concentration inside. Remember, we are mixing the fracture fluid with the propane. So we can always characterize the propane concentration, the concentration of the propane inside our fluid. So at each slurry stage, we are increasing the concentration of the propane. So we start with the part stage, we go to the slurry stage, we go to the flush stage, and then we go to our shut in. So these are basically the 3 steps in our pumping activity. All right, so design workflow. So at the end of our 3D modeling of the hydraulic fracturing, we expect to see something that looks like this, that should be able to give us a characteristics of what we expect. From there, we are seeing the propane concentration. We are seeing the concentration of the propane at each level within the hydraulic fracturing zone. Okay, so generally, this is our workflow for hydraulic fracturing activity. After you have drilled and you have collected data, you have to carry out our simulation. You bring the equipment, you bring the fluids on site. You have to rig up the pumping. That you have to build all those equipment that are required to do the pumping. You have to perforate production tubing. we have to flush and initiate formation breakthrough and all of that until right down. There are some situations where you may need acid treatment. You may need acid treatment before you continue with the pumping. All right. So these are our various stages. So remember, our first stage in our hydraulic fracturing exercise is the part stage. In our part stage, you have to pump. You pump fluid into the formation. So we have talked of thin fluid is pumped down the well. All right. So in our part stage, what happens is you pump only our fracture fluid with no propan there. You are pumping only the fluid with no propan there. So this fluid now is what we have: our slick water and linear gel. What is the objective? To enhance fracture dimension first. First, you have to create some initial fracture within that zone before you now have to pump in propan there. If you are pumping in propan when you have not created initial fracture within that zone, you will not going to achieve exactly what you have. So our fracture continue growing and propagating. So what you have to do is you pump, it grows and propagates right up to the level that has been predefined in our pumping schedule. Because in our pumping schedule, we must have defined also the time lapse and the volume of fluid that is needed in that particular level. Remember, at our part stage, there is no propan there. There is no propan at that particular stage. So after the part stage, you may now bring in our propan, the propan or the slurry stage, where you now have to mix the fluid now with our propan. And what is the objective of this stage? Stage from low to high propan concentration. That means as you're moving into the job, you are now increasing the concentration of the propan, as we have seen in our schedule. You are now increasing the concentration of the propan, as we have seen in that schedule. So it is stepwise. You're moving in stepwise. Place propan as per pumping schedule to obtain desired conductivity. So we start with the part where the fluid is injected. After the fluid is injected to the pumping schedule at the level where it is desired, we now have to go to the next stage, which is our slurry stage, and we start pumping it according to our pumping schedule, increasing the concentration of the propan as per defined by our pumping schedule. So this is exactly what is happening during the pumping schedule, during our slurry stage. You now remember we have our fluid that has been pumped there. As you pump the propan is coming in. It is now easy for the propan to now move into the fracture that have been created, because the first stage, the fluid goes in to create the fracture. The fracture definitely should be able to close up, but if you are coming in with the propan, which is not long after the first stage, you can now easily fill the propan into those fractures that have been created. The propan will go in, fill those fracture spaces, and then it comes now, and then at the end of the day now, it now gives the fracture some kind of a resistance so that it cannot easily close up. So after the slurry stage, you now have to do flushing. The flushing simply means that you are pumping fluid within the formation to push this propan into this particular formation. Because at the end of the slurry stage, we will have this, our well ball will be filled with propan. So you have to flush right up to a point where you have to force this propan here into our formation, so that there will be no propan in this zone. All right. After our flushing stage, we now have to shut in the well. You have to shut in the well for some time. And what is the objective? Allow fracture to close due to gel break and fluid leak up. Breaker is set to break 2 to 3 hours after fracturing job. Closure is fully closed around 3 hours after the job. Required shut-in time is 5 to 6 hours. So the entire objective of this stage is to allow equilibrium in the system, because you have created some kind of a disequilibrium. You now want to allow the system to readjust itself and then come to equilibrium with a new condition, so that you can easily know that, okay, this is my condition now. Because at the beginning, you may characterize it and you see that it has a high permeability and you are happy. But after a given time, remember, we are talking about a propan withstanding the closure stress, but you have to be rest assured that there should be some degree of closure that will take place. That one is for sure. So that's the reason why you are allowing the entire system to go into equilibrium, so that you should be able to give a good characterization of that particular system. Then you now have to clean up. Clean up simply means that you are now removing everything that you have inside this particular well ball, so that it is now ready for production. So from there now we can see the various changes in pressure within during the various stages. We have during the part stage, we have during the slurry stage, flush in, and during also the short in. We are seeing the variation in pressure, the variation in the pumping rate, and all of that. On this axis, we have pressure. On this axis, we have our pumping rate and all of that. Then here now, we are also having our propan loading, our propan concentration, propan loading, and all of that. So that comes to the end of a general look out of how the hydraulic fracturing exercise is going to take place. We cannot just go and start going to software and saying, click here, click here, click here. At the end of the day, you will not just even understand exactly what you're doing. You just know that you click here, click here, click here, and you have something at the end of the day, but you will not fully understand exactly what that something means. So if you have any question, you can ask. If you have any question, you make sure that you install your Frac Pro, so that tomorrow we are going to do our 2D simulation and also carry out 3D also. We are going to carry out both 2D and 3D simulation of hydraulic fracturing activity. So if you have any question, you can ask. If not, we'll meet tomorrow. All right, since there's no question, have a nice time. We'll meet tomorrow. Oh, Zero, you have a question? David, you have a question?
No, sir, no, sir.
All right.